Hello everyone, so thank you for being here. Welcome to this virtual talk about Greybox program synthesis. So just a few words about me. I'm Robin David. I'm a software security engineer at Quarks Lab, a French cybersecurity company. And I'm working on obfuscation, and especially deobfuscations, and many ways to automate bug discovery. Okay, so what is the agenda of today? I'm first going to give some definitions about obfuscation and synthesis. Then I'm going to describe our Greybox synthesis algorithms that we use for the obfuscations. And then I'm going to describe the implementations and the use cases on which we applied this approach. Okay, let's jump straight to obfuscation. What is obfuscation? We usually refer it to the means of transforming a program into a semantically equivalent program, but which is meant to be harder to understand. Why we do that? Mostly to protect intellectual property. So we do find obfuscation also in malware, but most of the time we find it in mobile applications, softwares from completely legitimate companies, and so on. So we less often see it in malware. So how we do that? So the idea is to, within a program, you want to protect the valuable assets. And what are the valuable assets in the program? Usually it's the program logic, so the algorithms, or the data. The data can be strings, constant, all these kind of things. So we usually separate obfuscation into two categories. The first one is the control flow obfuscations, where the goal is to hide the logic of the flow of execution. So at the bottom you see a small CFG of functions, and on the right the obfuscated versions of the exact same functions. So there's plenty of obfuscation for doing so, like virtualizations, flattening, opaque predicates, and so on. And otherwise, you have the second category, which is Dataflow obfuscation, which aims at hiding constant strings, keys, and so on. And for that, there's also plenty of different obfuscation techniques like data encoding, MBA that we are going to discuss, white boxes, encoding, and so on. So in this talk, we are going to focus on data obfuscations and more especially on MBA, which is mixed Boolean arithmetic. What is mixed Boolean arithmetic? Is the mean of scrambling expressions using so bitwise operators like XOR and OR and so on, and arithmetic operators like plus, minus, and so on. So here is so we have a small a plus b expression. And unobfuscated, we transform it with a semantically equivalent expressions, but that is more difficult to understand. So the questions from a reverse engineering point of view is, how do we get back the original expressions? And that is a difficult question because unlike control flow obfuscations, the answer is not Boolean. With control flow obfuscations, you sometimes want to negate branches, make sure, check that some of them are dead or so on, but here you really want to recover the original expression, and that is difficult. So obfuscations yields two distinct research problems. The first one is locating the data that you want to deobfuscate. And that's highly dependent on the targets that you're looking at, what you're looking for into the programs, what you want to attack or retrieve. So this is mostly manual, and this is also distinct for each target. And the second problems when you're deobfuscating programs, it's the deobfuscation itself. So once you've found the data that you want to deobfuscate. So how do you deobfuscate it? And synthesis only address this second issue. So you first have to find the data register or memory that you want to deobfuscate. So I wanted to highlight these two different issues in the deobfuscation. And now I'm going to describe what is synthesis. So synthesis is the mean of deriving, creating a program given high-level specifications and some additional constraints over it. For compilation, it can be faster program. For deobfuscation, it could be smaller or more readable program. So for program synthesis, so you usually have a programming input, and that program is the specifications. It encodes the semantic, the behavior that you want to preserve throughout the synthesis. So you give it to a synthesizer that optimizes some constraints like speed, size, or whatever. And then you obtain the new program which satisfy your specifications, so semantic and the constraints. So there is two main use cases for program synthesis. The first one is optimizations. And people doing optimization with synthesis usually call it super optimization. And there's two nice works for that. I recommend the super work made by John Rager and some folks at Google, and also Stoke. But we are going to focus on deobfuscation in this talk. But as one might notice, this is basically the same issue at the core level. You have a program and you want to make it more small, more efficient. So you're basically solving the same issues with both optimization and deobfuscation. Okay, so for deobfuscation, through synthesis, there is multiple approaches existing: templates, stochastic, search-based, enumerative, and so on. I'll give you a small overview of the work that has been done in the past. So the first works I've found about this is the work performed by Rolf Rolls in 2014. He is truly a pioneer in this field. Then there is the works by Ninon Herold, which was at Quarks Lab at that time, about spam. So spam is not truly synthesis, it's more like patterns and rewriting rules. But yeah, that's one of the first works targeting MBAs and giving some implementations for it. Then in 2017, you have the work of Cynthia that has been published at Usenix, and they use a stochastic approach using Monte Carlo search tree. I'm not going to describe that approach, but it's really interesting approach. Lately, in 2020, we did publish some academic results in an academic venue about our approach that we called QSynth, which is based on an enumerative search. And lately this year, there is some interest for MBAs and synthesis, so there is more works that have been published in Xynthia, MSynth, which is basically the implementation of QSynth using miasm by the same people of Cynthia, and Loki, which is more oriented on making obfuscation more resilient to synthesis. Okay, so what is Greybox synthesis? I'm going to describe the algorithm. So our approach uses two components, a symbolic executions and a synthesizer. So the basic workflow is that you have a program, you execute it symbolically, then you obtain some expressions that you want to simplify, you give it to the synthesizer, and hopefully you obtain some synthesized expressions. So we only use symbolic execution as a mean to obtain some Dataflow expressions. If you're able to retrieve expressions that comes from with a different approach, that's perfectly fine for us, because this is not the main of the algorithms. We just want to have expressions that we want to simplify. In practice, we do our symbolic execution statically or dynamically on the trace. That works the same. And so to give you a little overview of how it works, so here is a small MBA at assembly level. If you execute it with a symbolic executor, it will lift it to an intermediate representation, encoding the semantic. And let's say that you want to have the REX5 at the end here. What you're going to obtain is an abstract syntax tree of representing the REX5 value at that location. So our Greybox synthesizer takes ASTs of expression as input. That's really the input of the synthesizer. We have a huge AST and we want to obtain something which is smaller. And it's based on two components, the InputOutput oracle, which is our main contributions in terms of synthesis. So that's the black box components. I'm going to describe it. And we also have the AST simplification algorithms, which is the white box component. And so the idea is the following. You have your expressions, you try to synthesize from the root node. If you does not succeed, you're just going to iterate through the subnodes, trying to simplify opportunistically sub-expressions. And that's why you are going to have in and outs between the black box oracle and the AST simplification algorithm. So the purely black box approach, when we say black box, it's usually referring at comparing the input and output behavior of a program. So you're not considering the semantics, so that's a good thing when you're dealing with obfuscations. But you have a huge search space to look for, and the Boolean is the result is Boolean, because either you synthesize it all at once or you does not synthesize it at all. And on the other hand, when we refer to the white box aspects, it works for symbolic execution, fuzzing, and things like this. White box is manipulating the semantic of the expressions through its syntactic representation, which is usually the IR. And in our context, it means that you are going to manipulate the AST itself and the expressions, the operators that are being used, and so on. So the good point is that you consider the exact semantic of the expressions, but as we are dealing with obfuscation, we are hindered by the syntactic complexity of the expressions. So balancing between the two is really a good choice from our point of view. So now I'm going to describe a bit the input-output synthesis oracle. So let's consider here that you have A plus B, an expression that is known, and a black box for which you want to know what is behavior. What you are going to do is to generate some input vectors that give some valuation for A and B, and you are going to give them to the expressions. You're going to evaluate the expressions with those inputs, and then you obtain an output vector. And if at some point the values are all the same, what you can deduce is that the black box here is indeed doing an A plus B operation. So that's the basic idea behind black box input-output synthesis. And what we do to perform such computations, and this is the strength of our approach, is that we are going to pre-compute all the possible expressions, if we can say. So we take a grammar with some operators and variables, and what we are going to generate all the possible expressions up to a given bound, obviously. And we are going to evaluate those expressions on the input vector to obtain the output vector. And that gives us this mapping of output vector to the associated expressions. And so when you want to evaluate, to perform the synthesis of a given black box here, for instance, you're going to evaluate it. You obtain the output vector, and if you find it in your table, you know which expression it's encoding. And so the strength here is that you generate this table only once, offline, and then you're going to use it when you're synthesizing. The output vector, this approach is basically unsound, because if the vector is too small, you might miss some behaviors. But you can also check the equivalence to make sure that you're synthesizing something equivalent. But the question here is, what happens if you cannot synthesize the root node? And this is where the white box AST search is going to come into place. And the idea of iterating through the subnodes is to be able to synthesize obtain a partial synthesis of the expression. And here is the original strategy that we've implemented. So we were iterating the AST and replacing things that we've been able to synthesize, and at the end we substitute all of them and we obtain the resulting deobfuscated expressions. Some of you might have noticed here that we have some complexity issues because we are restarting from the root node at each iterations to iterate through the whole AST. So on huge AST that might be kind of complicated. We also experimented a few other strategies that was fixing those complexity issues. So the first one was a top-down approach, where we iterate through the AST only once. So it's like a divide and conquer. And as we go, we simplify the nodes that we are able to synthesize. It's not the optimal algorithm, but this is the fastest. And then we had the top-down and bottom-up approach, which was also replacing with placeholder variables. So V1 was the placeholders, and you do it recursively. So the algorithm is more efficient, and you obtain something which is more smaller than the simple divide and conquer algorithm. So we experimented with all these strategies. There's probably others to implement. And the questions that we had in mind is how many sub-expressions we were able to synthesize on the whole big AST. And so we made a small visualization of the algorithms to look at it. And as you can see, even though we are not able to synthesize the whole AST, at least we are able to synthesize many sub-expressions within this big AST. And this is where the Greybox combinations helps synthesizing expressions. We have some other examples here. Here at the top left, you have like an AST, which is something like 100,000 of nodes big. And as you can see, we are able to synthesize at many locations, and we reduce its size like significantly. And here is the result as a graphics. Okay, so now I'd just like to discuss the table generation process, which is also a critical part of our algorithm. So when you do generate all those tables, you have to evaluate millions of expressions in order to create this mapping from outputs to expressions. So what we did is two interesting thing is memorizations of the intermediate values. So for instance, a plus b will be only evaluated once, and then the result will be recombined with all the other operators and expressions to improve it, but we keep it in memory. And we're also using jitting to evaluate the expressions at native speed, because our implementation is in Python, but all the evaluation is made in C. So what we have been able to reach is like 25,000 expressions per second in terms of throughput. And we now have tables of 375 million entries, which is kind of satisfying. Where does we store them? At the beginning, we were using pickle files 1 year ago, but it only works for like 1 million entries because it takes time to deserialize a pickle object, so it was not sufficient. Then we tried like a relational model of database, but we either have the insertions or the lookup to be linear in the number of entries. So when you have millions and millions of entries, it does not work. So we ended up using LevelDB, which is a key value database made by Google, and that's working like a charm. And that ensures logarithmic lookup. And that was a constraint that we wanted to make sure to have. And we have, so the lookup in DB here is like in average like 122 microseconds, and if you realize that's really the synthesis time, the input, so you compute the output vector and the synthesis time is only like 100 microseconds. Then we made some experiments to try improving the representativity of tables that we were generating, and as mixing variables with operators is really done in a combinatorial way, sometimes expressions generated and are not optimal. So here you can see the kind of expressions that we do generate. And we tried using SymP to perform some linearizations of expressions. And what we obtain is the things on the right. So that's really great to further improve the size of expressions, but it completely kills the generation performances, and it has some other issues that makes it very difficult to use it in practice. So in practice, we don't use it, unfortunately. But that was a good trial. The second things that we do is expression learning. And that was based on some weird observations that we made during our experiment. Sometimes we were giving the synthesizer an expressions, and what was coming out is an expressions which was bigger than the input one. So we were like, what the fuck is going on? So when we looked at these expressions, it was actually expressions involving things that were not in our tables, so mostly constant. So this was our inputs and this was our outputs. So what we can do with that is basically we can update the table with the new expressions that we have just learned. So we have not been able to synthesize the expressions, but at least we have improved our table. That improved constants, and it means that over time tables can theoretically become better and better. So that's great. And by the way, for like generic constant like 1 and so on, we now introduce them in our table generation process, but we cannot enumerate all the constants, so we still can learn a new expression. Okay, so let's talk about benchmarks. So these are the benchmarks that we did for academic publications. We targeted binaries obfuscated with Tigress, and we did compared against Cynthia, against which we had like really good result. And since then, we kept improving our algorithm and implementations. So we still use the 4 datasets which are available online. We used, so EA is encode arithmetic, so it's basically MBAs. We also mixed virtualizations and MBAs, and on MBAs and encode data, which are all Tigress transformations. And so we have 4 benchmarks. The first line is the paper results, and as you can see, we kept improving things over time. And now we really have good, even better, if we can say, results. For instance, on the last datasets, we obtained like 90% improvements in terms of synthesized expression size. And in terms of speed, for some of them, we have like up to 67% improvements. I think it's the second one here. We turned to 2 minutes 49 seconds to 55 seconds. So that's great. And here we are talking about like 500 obfuscated expressions to deobfuscate. Implementations. We implemented that into the QSynthesis utility, which is our own implementations that we are releasing for this talk. QSynthesis is based on multiple other frameworks. The most significant one is Triton, which is doing the symbolic executions for us. We also integrated it into Qtrace, which is our own time travel debugger that we use internally at Quarks Lab, which is unfortunately not open source at the moment. And as I already mentioned, we use Dragon FFE, which is also developed at Quarks Lab for the digiting of expressions. We use LevelDB for the storage. We also integrated QSynthesis to IDA Pro. We use FastAPI to serve the tables to be able to perform some lookups as with a REST API. And I did not mention it explicitly, but what we wanted to have is, once you have the obfuscated expression, you want to have to re-obtain the final code, executable code. And for that we use Haribo, which is also developed at Quarks Lab, which is open source. That takes input Triton expressions, translate them to LLVM, and through LLVM Lite we are able to recompile the obfuscated expressions. And then I'm going to show you the integrations into IDA that we've performed, so it will give you a great overview of all that works. So here we have a small function, which is basically MBA that we want to simplify. We are going to launch QSynthesis, and we're going to ask to synthesize from here to the end of the basic block. We ask here to synthesize the register RAX. We are going to load the tables that we want to use. Then we just run Triton, the symbolic execution, to obtain the expressions. So here the expression is 124 nodes big and contains 3 different inputs, like RGI, RCX, and RDX. We can highlight the dependencies and we can see here that all the instructions are involved in the computations of the RAX value at the end. We can look at the AST that we obtained, which is not that big actually. And then we just have to run the synthesis, and that's almost instant. Here you can see that this is the resulting expressions. We reduced its size by 92%. And we can visualize the AST, which is kind of small. And so what we want to do here is basically we want to reassemble the obfuscated expressions back to assembly. And this is exactly what we are going to do here. So we are going to call Haribo, which is going to call LLVM Lite, which is a binding for LLVM. So we recompile the expressions and we obtain compiled code. So here we are going to patch the function bytes, shrink the functions because it's only in a single basic block and we can do it. And there it is. We just patch back the instructions, only the instructions that are involved in the computation. So we kept the prologue and epilogue. And here you can see the expressions with the XOR, add, AND, which are the deobfuscated expression. So that was for the demo, showing you how we do use it. And now we are going to discuss the use cases on which we tried our implementation. So we first tried on Yanso LLVM, which is an obfuscator LLVM derivatives that was published last year, and that is actually really a decent obfuscator. The obfuscations are kind of great. There's multiple of them, but we are going to focus on the VM and the obfuscate constants. So the VM is basically going to replace arithmetic operations and bitwise operations with calls to functions that are going to do them. So you can see here the handler for the add. And for synthesis is like almost instant. In this case, we can just synthesize it. And what we obtained in our case is the functions, which is basically LEA, RAX, RCI plus RDI and RET. So yeah, that's pretty straightforward for the synthesizer. They use multiple MBAs, and they also use MBAs to obfuscate constant. And so I would like to give some precisions on constant. So there's two cases. Either you have expressions that are using constant like a and dead beef. We cannot synthesize such expressions unless you have this constant in your tables. But as you cannot enumerate all the possible constants, you probably don't have this constant, and you're not going to be able to synthesize the expressions once it's diversified. But what we can do is that we can synthesize constants themselves. So opaque constant is going to take a constant and to introduce some spurious variables and perform some MBAs to compute the constant. But that we can synthesize it. And this is a small example that we have generated through Yanso LLVM. And the idea from a synthesis point of view is that you take the expression, if you evaluate it on all the inputs and you always obtain the same output, it means that the inputs does not perform any modifications on the resulting value. And that means that they are not used and that you are basically encoding a constant. So during the synthesis process, if the output happens to be always the same for all the inputs, we know that we are on a constant, and we can just evaluate it to obtain the associated constant. In this case, it's just 0. The second use case that we've looked at is the Windows kernel, and especially some patchguard functions. So those functions in the kernel are known to be obfuscated with a framework called Warbird. So I've not looked into details into that, but a colleague pinpointed me that this function, and I've looked at the code on it. It's true that it seems to contain like weird arithmetic operations that could probably be simplified. I don't know whether it's MBA or not, but we can do few things about this. And here is a small example of the result in the IDA plugin. So we executed this basic block, for instance, which was yielding this AST, and we were able to synthesize it to something smaller, which the resulting assembly is the following. So I've not looked that much into details, but I recommend you to look at the two links that are on the slide if you want to know more about this obfuscator. And then the last use case that we've looked at is some messaging application that are being used by youngsters mostly to send ephemeral messages. And it does contain lots of MBAs. That's good for us, and we can try to deobfuscate them. And actually, so here is a small example for ARM64, where it generates like a huge AST with 5,000 nodes with one input, and it's actually encoding a constant like 0x7b2. So we are kind of happy with that. We've been able to synthesize multiple of them. But yeah, once again, it would require like a more in-depth research to know what these MBAs were used for. Okay, quick conclusions. So our Greybox algorithms is like a good balance between the black box and white box aspects, because we can opportunistically synthesize sub-expressions while pure black box cannot. We still have issues that most approaches have, like to target the expressions using constant, but we do have ideas on how to address them. And as takeaways, so breaking obfuscation is still crucial, it's still the first step that you have to do before doing further reversing. Synthesis only address a sub-part of the deobfuscation process, meaning that it's able to synthesize, to simplify expressions once you've located them into the program. So you first have to solve the first issue, which is finding what you want to deobfuscate within the program, and that's always the most difficult part. We also use it to synthesis to assess our own obfuscator, which is called Quark Shield, and that allows us to continuously improve it to make sure it's the obfuscation we generate is resilient. And like usual, what makes an obfuscation potent is carefully mixing it with other transformations. An MBA taken alone can usually be broken. And last, I would just want to do some acknowledgement to Luigi Coniglio, who kickstarted that approach in our dynamic tracing framework, and Jonathan Salwan, with whom we tweaked Triton to make it more efficient on this kind of use cases. And that's all for me. If you have any question, do not hesitate to ask. Feel free to ping me. I would be happy to answer any of your questions. So thank you very much.